This research introduces a novel solution method for stochastic differential equations, SDEs, using quadratic polynomials. By subdividing the time interval into subintervals and approximating the solution between two successive intervals with quadratic polynomials, the proposed approach addresses the computational challenges associated with models based on SDEs. The main properties of the stochastic numerical methods, such as convergence, consistency, and stability, are analyzed in detail. The efficacy of the proposed method is demonstrated through its application to an SDE problem, yielding promising results. SDEs are essential in modeling real-world phenomena involving random noisy perturbations, which cannot be captured by ordinary differential equations, ODEs. Applications of SDEs include theoretical physics, molecular biology, population dynamics, and mathematical finance. Time-discrete approximations on digital computers are the most effective and widely used method for solving SDEs, involving discretizing the time interval into finite steps and iteratively generating approximate values for the solution process at these points. Existing numerical schemes for solving SDEs, such as explicit stochastic orthogonal Runge-Kutta-Chebyshev schemes and local linearization approaches, have shown success in terms of convergence order, mean square stability regions, and computational costs. The novel approximation method proposed in this research uses quadratic polynomials to approximate the solution between two successive intervals. The authors analyze the main properties of this stochastic numerical method, including convergence, consistency, and stability. They test the proposed method in an SDE problem and report promising results. This paper contributes to the development of efficient numerical methods for solving SDEs, crucial for various applications in science and engineering. The proposed method offers a new perspective on solving SDEs using quadratic polynomials, providing an alternative to existing numerical schemes. The authors introduce a novel approach to approximate stochastic differential equations, SDEs, by incorporating a deterministic error correction term. This work builds upon previous research, including the explicit Steklov mean M scheme proposed in 24, and the implicit split-step linear Steklov mean scheme developed in 25. The manuscript focuses on the Ito SDE, 1, with initial condition, 2, where the coefficients f and g are locally Lipschitz. The solution x, t, is defined on a probability space with an increasing family of sigma fields, and the stochastic process, x, t, w, t, satisfies the properties outlined above. The authors review classic stochastic schemes, such as the Euler-Maruyama, M, method, 5, and the Milstein method, 6, which approximate the solution to the SDE using a discretized timestepping approach. The M method uses a simple first-order approximation, while the Milstein method incorporates a second-order correction term. The manuscript is structured into main sections. Section 2 describes the development of the algorithm using quadratic approximating functions. Section 3 analyzes the stability, consistency, and convergence of the proposed method. Section 4 presents numerical results testing the validity and effectiveness of the proposed strategy, and Section 5 discusses the obtained results and future work. The authors also introduce the equation for geometric Brownian motion, 7, a special case of the SDE, where the drift and volatility terms are proportional to the current state x, t. This equation is used as a test case to demonstrate the proposed algorithm. Equations 1 and 4 define the SDE and its solution, respectively. The author's approach aims to improve upon existing methods by incorporating a deterministic error correction term, which is expected to enhance the accuracy and stability of the approximation. The use of quadratic approximating functions in Section 2 is a key aspect of the proposed algorithm, and the analysis in Section 3 will provide insight into the method's performance. The manuscript assumes a high level of mathematical sophistication, and the notation and terminology used are specific to the field of stochastic processes and SDEs. The author's goal is to develop a novel algorithm for approximating SDEs, and the manuscript provides a detailed outline of the methodology and analysis. A novel method for integrating a system over a time interval, 0, t, is presented, utilizing a regular partition O equals t0 less than t1 less than t less than. less than Tn equals T, where n is an even number. The partition is defined by T equals I delta T, allowing for evenly spaced time steps. The objective is to obtain the values of the function x, t, at the next two time steps t2n plus 1 and t2n plus 2, given approximate numerical values for x, t, at the grid points t, I equals 0, 1, 2n, for t less than t. The method involves integrating equation 7 on the interval t2n plus 2 to derive equation 8, which relates the values of x, t, at t2n and t2n plus 2. A quadratic interpolation function, given by equation 9, is used to approximate x, t, in the interval t2n plus 2. This approximation is based on the quadratic interpolating function psi n, j, t, j equals 2n plus 1, 2n plus 2, defined by equation 10. Substituting the approximation 9 into equation 8 yields equation 11, which is then simplified to equation 12. However, equation 12 requires the values of x, t, at t2n plus 1 and t2n plus 2, which are not yet known. To address this, the same technique is applied to the interval t2n plus 1, integrating equation 7 to obtain equation 13. Equation 13 provides a formula for the value of x, t, at t2n plus 1, which can be used in conjunction with equation 12 to determine the values of x, t, at t2n plus 1 and t2n plus 2. This method relies on stochastic integrals, quadratic interpolation, and the properties of Wiener processes, as represented by the terms W2n and delta W2n. The use of quadratic interpolation functions psi n, j, t, enables the approximation of the solution x, t, at the next time steps, while the stochastic integrals in Wiener processes capture the uncertainty and randomness inherent in the system. The regular partition of the time interval, 0, t, allows for a straightforward implementation of the method. The equations derived in this section will be used to develop a numerical method for solving the system, which will be presented in subsequent sections. Potential assumptions in future work may include investigating the accuracy and stability of the method, as well as exploring alternative interpolation techniques and time-stepping schemes. The approximation of x, t, in the interval t2n plus 1, is achieved through quadratic interpolation functions, which are defined as a combination of quadratic interpolating functions psi n, j, t, where j equals 2n plus 1, 2n plus 1. These functions are calculated using equations 15, resulting in the expression for x, t, given by equation 14. Substituting this approximation into the original stochastic differential equation 13, we obtain equation 16, which can be solved for x2n plus 1 and x2n plus 2. To solve these equations, we utilize the previously known value of x2n and the relationships between x2n plus 1 and x2n plus 2, as expressed in equations 19a and 19b. The coefficients alpha n and beta n are defined in terms of the model parameters micro, sigma, and the random variable w2n, which represents the increment of a Wiener process over the interval t2n plus 1. Continuing this process, we progress the integration until reaching the final time t. This approach allows for an efficient and accurate approximation of the solution to the stochastic differential equation, enabling further analysis and understanding of the underlying system's behavior. The authors conduct a stability, consistency, and convergence analysis of their proposed method for approximating solutions to stochastic diffusion equations. They define mean square stability as a sequence xn infinity n equals 0 that satisfies lim n right pointing arrow infinity sign e xn 2 equals 0. A theorem is presented, stating that under certain conditions on the parameters, the proposed method is stable in mean square. The proof involves analyzing the expression for x2n plus 2, derived from the proposed method's equation 19b. This expression is used to establish a condition for mean square stability, given by equation 23, which requires that the sum of terms involving parameters micro, increment t, and sigma be less than 1. Applying the expectation operator e2 to the expression for x2n plus 2, utilizing the independence of Wiener increments, leads to equation 22, a recursive relationship between x2n plus 2, and x2n, 2. By using this recursive relationship in equation 19b, the authors derive the result that lim n right pointing arrow infinity sign x2n plus 2 equals 0 if the condition in equation 23 is satisfied, demonstrating the stability of the proposed method. This result is crucial for ensuring that the numerical approximation does not diverge over time. The author's analysis provides a rigorous foundation for using their method to solve stochastic diffusion equations, highlighting the importance of parameter selection to maintain stability. The authors derive a condition for stability, which is necessary for the mean square convergence of the proposed method. This stability condition is given by equation 26, involving the parameters micro, increment t, and sigma. A sequence, xn, is said to be mean square consistent if the local error satisfies equation 27, where c and p are positive constants. The authors then prove theorem 2, which states that the proposed method in equation 19 is mean square consistent for approximating the solution of the stochastic diffusion equation in equation 7. The proof involves expanding the exact solution x, t2n plus 2, using the Ito formula, given by equation 28, and comparing it with the locally approximate value x, t2n plus 2, obtained from equation 11, as shown in equation 29. This result highlights the efficacy of the proposed method in accurately approximating stochastic processes, a critical component in understanding complex systems. The authors derive an upper bound for the mean square error of the proposed scheme, denoted by delta 2n plus 2. By applying the interpolation error formula, they obtain an inequality, 30, that decomposes the error into two terms. The first term is bounded using the interpolation error formula, resulting in equation 31. The second term is approximated using the Taylor expansion of x's around t2n, as shown in equation 32. Taking the limit as the time step increment t tends to 0, the authors prove that the mean square error delta 2n plus 2 is bounded by k increment t, where k is a constant, thus establishing the consistency of the proposed scheme in the mean square sense. A similar result is obtained for delta 2n plus 1, with an upper bound of k increment t. The authors remark that, in conjunction with the previously established stability results and the stochastic version of the Lax-Richtmeier theorem, the proposed method is conditionally convergent for solving stochastic differential equations. The paper then proceeds to present numerical results, where the performance of the proposed numerical technique is evaluated for solving stochastic differential equations. The errors are measured using the L1 error, L2 error, and L infinity error between the approximate and exact solutions, defined as the average absolute error, root mean square error, and maximum absolute error, respectively. The authors of the study examine the performance of their proposed scheme for solving stochastic differential equations, specifically focusing on the form dx t equals micro x t dt plus sigma x t dw t, with an initial condition x, 0, equals 1. The exact solution to this equation is given by x, t, equals x, 0, micro sigma squared, 2, t plus sigma w, t. In their analysis, they set sigma equals 0.5 and assume micro equals 1. Demonstrating the stability region for their method in Figure 1, which is comparable to the stability regions of the implicit M and Milstein methods shown in Figure 2. The authors then illustrate the stochastic solution using their scheme, alongside the exact solution, for various time steps increment t equals 2 to the power of 8 in Figure 3. They report the L1 error, L2 error, and L infinity error in tables 1, 2, and 3, respectively, showcasing the consistent decrease in error under mesh refinement, thereby satisfying the stability condition. Notably, their method outperforms the implicit M and Milstein methods. Subsequently, they present the numerical solution with micro equals 1 in Figure 4, which exhibits unstable sample paths, corroborating the theoretical stability conditions. The stability region is determined by equation 26, and the author's computational results validate the theoretical stability conditions, underscoring the efficacy of their proposed scheme in solving stochastic differential equations. The authors visually compare the stability regions of the proposed implicit Euler-Maruyama (M) method and the Milstein method in Figure 2. The stability region, depicted as a shaded area, represents the parameter space where the numerical method remains stable. For a specific sigma value of 0.5, the implicit M method exhibits a larger stability region than the Milstein method, indicating that it can accommodate a broader range of step sizes and noise intensities while maintaining stability. This improved stability is attributed to the implicit treatment of the drift term, which reduces numerical error amplification. Figure 3 demonstrates the accuracy of the proposed method by comparing the approximate solution obtained using the implicit M method with the analytical solution of equation 35. The close agreement between the two solutions validates the efficacy of the proposed method in approximating stochastic differential equation solutions. The implicit M method is based on the Euler-Maruyama scheme, where the drift term is treated implicitly, leading to a nonlinear system solved using fixed-point iteration. In contrast, the Milstein method employs an explicit treatment of the drift term. The stability analysis of the proposed method is facilitated by deriving the mean square stability condition, expressed as a function of step size, noise intensity, and problem parameters. The authors demonstrate that the proposed method satisfies this condition, ensuring the stability of the numerical solution. Overall, these results highlight the advantages of the proposed implicit M method in terms of stability and accuracy, making it a promising approach for solving stochastic differential equations. The authors present a comprehensive evaluation of the proposed method for solving equation 35 through a series of numerical experiments. Tables 1, 2, and 3 display the L1, L2, and L-infinity errors, respectively, obtained using the proposed method, implicit Euler-Maruyama (M) and Milstein methods for various values of n. The results in Table 1 indicate that the proposed method outperforms the implicit M and Milstein methods in terms of L1 error, with the smallest error achieved when n equals 2105.0966 times 10 to the 5. Similarly, Tables 2 and 3 reveal that the proposed method exhibits superior performance in terms of L2 and L-infinity errors, respectively. A visual representation of the proposed method's performance is provided through Figure 4, which showcases the results of 10 simulations for micro equals 1. This figure illustrates the method's stability and accuracy in approximating the solution to equation 35. Notably, the proposed method demonstrates a significant reduction in errors across all three norms, L1, L2, and L-infinity, as n decreases, indicating its robustness and efficiency in solving stochastic differential equations. In contrast, the implicit M and Milstein methods exhibit larger errors, highlighting the limitations of these approaches. These findings underscore the advantages of the proposed method in terms of accuracy, stability, and computational efficiency, making it a promising tool for solving stochastic differential equations in various applications. The authors present a novel methodology for numerically solving stochastic differential equations, focusing on stability, consistency, and convergence. This approach involves subdividing the time interval into subintervals and approximating the drift term using quadratic polynomials over 3 successive node points. The numerical scheme is analyzed in detail, with its properties including stability, consistency, and convergence thoroughly described. The methodology is illustrated through numerical examples, which demonstrate improved performance compared to the implicit M and Milstein schemes. The authors acknowledge the significance of extending this method to the general form of stochastic differential equations in future work. They provide a comprehensive list of references, further supporting the validity and potential of their proposed approach. This research contributes to the advancement of numerical methods for solving stochastic differential equations, offering an innovative solution that addresses challenges related to stability, consistency, and convergence. The proposed method's improved performance in comparison to existing schemes underscores its potential impact on various fields that rely on these equations, such as finance, biology, and physics. Solving stochastic differential equations, SDEs, is crucial in modeling complex systems that involve uncertainty and randomness. Stiff and ergodic SDEs pose significant numerical challenges, as traditional methods may struggle to achieve accuracy and stability. Recent research has focused on developing advanced numerical methods to address these challenges. Existing numerical methods can be broadly classified into several categories. Firstly, there are Monte Carlo-based methods, such as the Euler-Maruyama and Milstein schemes, which rely on random sampling and have low computational costs. However, these methods often suffer from low accuracy and may not be suitable for stiff systems. Another category is the finite element method, which discretizes the spatial domain and uses Galerkin projections to solve the SDE. This approach can be computationally expensive but provides high accuracy. The authors also discuss the use of spectral methods, such as the Karhunen-Loève expansion, which can efficiently capture the stochastic dynamics of the system. Furthermore, the authors review the use of exponential integrators, which are designed to solve stiff SDEs efficiently. These methods exploit the structure of the SDE to reduce computational costs while maintaining high accuracy. The authors also discuss the application of machine learning techniques, such as neural networks, to solve SDEs. The review highlights the strengths and limitations of each numerical method, emphasizing the trade-offs between accuracy, computational cost, and stability. The authors also discuss the importance of ergodicity, which is crucial for accurately capturing the long-term behavior of SDEs. A novel finding of this review is the use of geometric integration techniques to solve SDEs with complex geometry, such as those involving irregular boundaries or obstacles. A limitation of existing methods is their dependence on ad hoc tuning parameters, which can be difficult to calibrate in practice. Future research should focus on developing more robust and adaptive methods that can handle a wide range of SDEs with varying degrees of stiffness and ergodicity. Overall, this review provides a comprehensive overview of existing numerical methods for solving stiff and ergodic SDEs, highlighting both the progress made and the challenges that remain. The authors present a thorough examination of existing literature on stochastic differential equations, emphasizing significant contributions and methodologies. They commence by referencing Diaz-Infante and Jerez's work on the linear Steklov method for SDEs with non-globally Lipschitz coefficients, which achieves strong convergence and efficient simulation. This is followed by the discussion of the Runge-Kutta method for SDEs, as proposed by Burrage and Burrage, which demonstrates improved stability and accuracy in solving SDEs. The paper also highlights the work of Kahl and Schilling, who developed a new family of Runge-Kutta methods that exhibit better performance in terms of stability and convergence order. Furthermore, the authors delve into the realm of adaptive time-stepping algorithms, citing the work of Rossler, who proposed an adaptive Runge-Kutta method that dynamically adjusts the step size based on the local error estimate. This approach has been shown to significantly enhance the efficiency and accuracy of SDE simulations. In addition to these methodologies, the authors touch upon the importance of stochastic collocation methods, as demonstrated by the work of Zhang and Gunzberger. These methods leverage polynomial chaos expansions to approximate the solution of SDEs, providing a powerful tool for uncertainty quantification in stochastic systems. The paper concludes with a discussion on the challenges and future directions in the field of SDEs, including the need for more robust and efficient numerical methods, particularly in high-dimensional systems and those involving non-smooth coefficients. The authors emphasize the importance of interdisciplinary collaboration to advance the understanding and application of SDEs across various fields.